Okay, so you'll remember that a free body diagram is simply a diagram that shows you all the different forces that are acting on an object. And the object can be just drawn as a rectangle. And remember that I said yesterday, Cole, the labeling wasn't so important, but you still have to label. It's just that your labels don't necessarily have to match mine or someone else's. So let's begin. A rightward force applied to a book in order to move it across a desk with a rightward acceleration. Consider friction, neglect air resistance, diagram the force acting on the book. So we are on a desk, and I traditionally draw that. So I'm just going to draw that. And all of these things are likely happening on Earth. So we'll do that. And if it's on a surface, that means we've got what?
Normal.
A normal force. And I need to do an orientation on my pen here right away. And it's a rightward force that's applied. There is an acceleration. So what does that mean? I guess it would have to be moving, yeah. It's a rightward acceleration.
The force pulling it is bigger than the friction.
Correct, Leo. So we want to show the applied force, the FA. Having a hard time here because it doesn't line up with where I'm putting it.
I have a question.
Okay.
Does that mean that we're supposed to put FM and FW on all of them?
No, because the normal force, Jeff, is only there if there's a surface holding it up. So if it's like an object falling, then there's no normal force, right? But FW will likely be on every one because every one of these is going to happen on Earth, right? Yep, that's fine. FA, applied force. How are you supposed to remember all this? Now I do. Thanks. Again, backpacks, whoops. Backpacks exist on Earth, so weight force. It's a single strap, so it's not a normal force, but what are you going to call it?
An applied force.
It could be an applied force. I would take that. I would also take, some books would call it a tension force. Either one of those would be fine. Right?
We have to define what we call them.
No, but I mean, you're going to end up using the same conventions that I use, is what you're going to end up doing. Right? Only in very weird conditions, like if you've got some force that's applied by some object, you might label it with that object. But most of the time, you're going to use the same conventions that I use, because they're going to happen over and over again. A skydiver is descending with a constant velocity. Consider our resistance, diagram the forces acting on the skydiver. Skydivers jump out of planes on Earth. Weight force. Yeah.
Are the majority of questions going to be on Earth?
Yes. Pretty much. Unless it specifically says a skydiver jumps out on the planet Pluto. Is there still going to be gravity?
Yeah.
It's just going to be smaller, that's all, yeah. Okay, so there's air resistance here, and Sarah asked about when do we know if they're balanced. It's when the forces are constant velocity, so we're going to have a force up, and what are you going to call it? Air resistance? F air or FF?
Would it only be the solid and that are equal?
Yep. Is there any sideways here? No. They could be. F normal, which means it's on a what's it could be. There could be a sideways force due to wind, and it could be equal to those, but it doesn't have to be, right? Something could be moving horizontally and accelerating, but not accelerating vertically, right? They are independent of each other. That's actually something we were just talking about in grade 12, about how those forces, the component forces, are independent of each other. Okay, number 9, a force applied to the right to drag a sled across loosely packed snow. Do you get the feeling that loosely packed snow means something? It means that there is friction involved. A rightward acceleration. Diagram the forces. So, weight force, normal force, rightward acceleration means big force to the right. Loosely packed snow is code for there's some friction. These are relatively easy once you get into it. We're going to get to the problems right away. There's no units here. Oh, the labels, you mean?
Yeah.
Yeah. Like everything, it takes practice, right? Like everything. A football is moving upwards towards peak after having been booted by the punter. Neglect air resistance, diagram the forces acting upon the football as it rises upward toward its peak. Football is played on Earth. Weight force. Space football, yeah. Anything else? Any other forces? Says neglect air resistance. Cole, I need you to listen here. This is an important one. Any other forces that someone wants to add in? Mervin? Upward? Like this?
Yeah.
And like that?
No.
No. Oh, the right side.
You want just this?
It's like that video that we watched.
And it's all-
And so you want this one and this one,
Yeah.
but not this one.
Yeah.
All of that is wrong.
You guys don't put an arrow on the side.
Nope, that's it.
What?
There's no guard force?
Neglect air resistance. A football is moving upwards towards peak after having been booted.
Oh my god.
After. Once it's left my foot,
There's no force.
what's on it? What force is on it?
There's no guard force.
Just gravity. My foot is no longer touching it. In fact, the longer you keep your foot on it, remember the whole thing the guy was kicking, right? Follow through, right? But once it leaves your foot, unless you're a Jedi, there is no more force.
Well, if I'm a Jedi.
But you're not Ty,
It would be like this, right? It'd be the top and the side.
I suppose,
Okay. Like
if you were a Jedi.
Okay. If it was like as he's kicking the ball, would it be?
Now, as you're kicking the ball,
Would it be angle or would it be top and side?
yeah, as you're kicking the ball, it'd be like that.
You don't do top and.
No. Well, you would kick it like that, and then there would be like what we call components. Part of that would be sideways, and part of it would be up. Vectors.
So you.
That's for another day.
One angle line though.
Yeah, that's for another day.
Okay.
This football, only that.
When since you start force, it was like Jedi, just Jedi.
Do you have Jedis in Brazil?
Of course they do.
A car is coasting to the right and slowing down. Diagram the force acting upon the car. The car is acting on a surface like a road. We have weight force. We have normal force. It is coasting to the right and slowing down. So the only sideways force acting on it is friction. That's the only sideways force there is. Now, I've had kids argue with me because they say, well, even if the engine's running, there's a little bit of an applied force. I will accept that as long as your applied force is smaller. Okay? Free body diagrams, we're good? Alrighty, so you had a little break there. I got other 4 sample questions, is that right? Okay, so it won't take me too long, maybe 10 or 12 minutes. I'm going to remind you of some of the conventions that we came up with for doing word problems, right? You want to sort of identify what you know, try to figure out the formula, write the formula, right? Line up your equals, substitute, use units, all that good stuff. Basically, again, you're convincing me, you're selling me that you know what you're doing. Well, if you don't, then that's what I need to know, right? So that I can make you better. A constant force acts on a 12 kilogram mass and changes its velocity from 4 to 18 meters in 3.5 seconds. What is the force? Okay, so let's start by drawing this free body diagram. And eventually, on some of the easier ones, you'll realize I don't really need to draw that. You just get the picture in your head, right? But let's draw it for now. Constant force acts on a 12 kilogram mass, change its velocity. What is the force? So we've likely got an object. It doesn't say that it's on a table, but it doesn't say it's not. It doesn't give us a whole lot of information, really, does it? We can probably presume it's on Earth, and there's a weight force, and there's a normal force. But it appears that neither one of those is actually doing anything, right? Because it's just moving sideways. So do you even need to draw those? Well, from a technical standpoint, yeah, you should. I'm okay with letting you just let it slide for a little bit. Junior, you missed the part of the video where it said, rip the cords out of your ears.
Yeah.
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 Because you weren't listening to it, maybe.
What do you have to
That would be the irony part that I was talking about earlier. So we got a constant force. Now, what kind of force is that? Doesn't say, right? But it's a force that is, and it's likely applied, right? Something is applying a force, FA. FA. Something is applying a force. Is there any friction here?
Yes.
Doesn't say that. It says there's no friction. Doesn't say there's friction, so you have to assume that it's frictionless.
Why would it be frictionless though?
Because you just assume.
We're just starting with simple ones. That's why. Right? We're just starting with simple ones. Okay. Now, actually, I probably should backtrack a little bit. What formulas do we know? We know F net equals MA. That's Newton's second law. And what do you think this one here is? Well, I haven't really talked a whole lot about it, so let me take a moment. What does F net stand for, Cole? What does F net stand for? What does it mean? What does F net stand for? What does the net mean? The net force. When you have net pay, you know, like when you're working, you got your gross pay and your net pay. What's net pay?
After they take all your stuff.
After they take your deductions. It's the sum, Brandon, right? It's the sum of your pay plus all the deductions, which are all negatives, right? So the net force is the sum of all the forces. In this case, all we've got is applied force and friction force. But in our particular case right here, the FF is 0, isn't it? Right? There is no FF here. In fact, in this case, in a frictionless situation, the net force is equal to the applied force because there are no other forces. Okay? Yeah. We'll get to that. Okay, so we know that F net is equal to MA. Do I have the mass? I do. Do I have the acceleration?
Yeah.
I do not.
Well, you have a velocity.
I do not. It changed its velocity from 4 to 18. So the 4 is the VI, the initial, and the 18 is the VF, and our time is 3.5 seconds. Can I get the acceleration from the VI, the VF, and the T? You betcha. Have you sort of pictured it in your head what the first step is going to be? This is going to be the last step.
You got to find
I got to find the acceleration. Acceleration is delta V over delta T. So the first step is really find the delta V. Yes, they're getting a little bit hard. This is a 3-step, Ty. Are you going to write this down, Ty?
Yeah.
Okay, because I don't see a pencil in your hand. Delta V is equal to VF minus VI. The change in the velocity. And how do you know how to do this? It takes practice. It's not going to come right away. You can't bench 300 pounds without starting out with 50.
Wow.
Final velocity, 18. Initial velocity, 4. Change in velocity, hopefully no calculator required, 14. Please tell me no calculator required. Although I see people typing in 1 times 12 on calculators, just to be sure.
Well, sometimes I do it just to be sure.
Well, my mind is in the test mode, and I'm just thinking about trying to get things like I got my calculator.
Even if it's like
1 times 12.
I'm still gonna.
Yeah.
I'm still gonna do
Oh, that's pretty sure.
It's like you're already.
Mine's so gamble, you just gotta think. Hey.
it. No, no, we do it.
Next, okay, let's not talk about calculators. Next step, find the acceleration. A equals delta V over delta T, so that's going to be 14, and our time is 3.5.
This is easy.
Yeah. 14 divided by 3.5. Now that you need a calculator for. Unless you know that 3.5 times 2 is 7, and there's 2 7s in 14, so that means 14 divided by 3.5 is 4.
Very easy.
How did you do that one?
I took 3.5 and I multiplied by 2 in my head,
Yeah.
and I got 7. And I know that 14 divided by 7 is 2. And how many 3.5s have I got in a 7? 2. So 2 times 2 is 4. And now I'm going to go F net is equal to MA. My mass is 12. My acceleration is 4. How do you do 12 times 4 in your head?
You just know it.
Well, some people will, but you,
Let's say 48.
yeah. Here's how I would do it. Times 12, you take 10 times 4 is 40. And then you got 2 more times 4 is 8. 40 plus 8.
Like 12 times 2.
Or you just know it.
Okay.
12
48 newtons. And because there is no friction, therefore the applied force is also 48 newtons.
What if there was a friction? You have to
Oh, we're going to get to those right away.
Wait, how do you, wait, what?
Because because there's no friction, the net force is the applied force.
So you only had to find the velocity and put it into the other force.
Oh.
Yep.
Yeah.
So F equals 48.
Okay. Now, are you seeing how these are a little bit more steps than we did before, right? I'm doing the old, it's kind of the reverse Russian nesting dolls. I'm kind of adding them on. Instead of pulling them apart, I'm putting them together. Okay. This time, we're going to kind of do it in reverse. If you guys have this picture, I don't think you do. Okay, good. You can. Example number 2, Cole. Stay with me, man. Don't lose sight. The game is still on, right? Hang with me here, Ty. 2 kilogram block is being pulled by a rope as shown. 25 newtons of force are being applied, and the friction force is 5. What is the acceleration? And if the force applied for 4 seconds, determine the velocity. So there's more to it here. Brandon, you staying with me? Hang with me here, man. The first step is to find the acceleration. What do I know? I know that my 25 is my applied force, and I know my 5 is my friction force. And usually when you have a bunch of forces, you're going to have to add them together to find your net force. Okay, so the 25 is the applied and the 5 is the friction.
Does it matter if I change the forces? Like, because I don't like that way of showing the work. Because, like, that way it's kind of,
Can you show me what you want to show?
like, put the 25 on the other side and 5 on the
You want it going to the left?
No.
Oh, you want this.
Like,
Yeah.
Well, I will say
You know,
that.
that's, I don't know in this case because it's a rope, but
Oh yeah.
other, like, on other,
I will say this. The convention is, regardless whether it's a push or a pull, you always draw it as a pull. That's convention. Will I understand what you're doing? Yeah, but
Don't do it.
no. You'll have to. You won't see me ever do that. Get over there. Okay. So what's the first step? The first step is to find the net force, and F net is equal to FA plus FF. And I want you to use the plus because F net merely means add up all the forces. And the reason I want you to do that is because when we get into 2-dimensional, you have to do vector addition.
Whoa.
Yeah? Okay, so I want you to think about it being a sum, a vector sum. And so the applied force is 25, but we're going to add what? -5. Why -5? Because the vector direction is to the left. Sorry, to the left. Does that make sense? Yeah, and it just takes practice. No different than really anything that I know.
yeah, what's that thing?
F net.
There you go.
F net.
I mean, if you just listen,
You could do that too, Brett. Glad you picked up on that. So the net force is 20. F net is equal to MA. Some of you maybe have gone ahead already. The net force is 20. The mass is 2. Please tell me you can do this part in your head. 20 divided by 2.
My sheet just says a block. It
Oh,
doesn't
yeah?
say it's just a week.
Oh, really?
So that was confusing.
So that it would be, yeah. So you have to add that. So what I likely did was I made the change and I just didn't print the new sheet. Thanks, AJ. So make sure you note that it's a 2 kilogram block. So the acceleration is 10 meters per second squared. And now if the force applied for 4 seconds, determine the velocity. Let's label this part B so that I know that you know what step we're doing here. And now we're going into velocity, and so now we're going to use A equals delta V over delta T.
don't like this.
No? I hate to tell you this, but there's a lot of this in physics.
Yeah, I did last.
It's kind of like saying, I don't really like that music in band class.
Well, you can.
You know, all this metal and welding, I'm not really keen on.
You can change this like on music in band. Like you could just hate a certain piece.
That's
Fair enough. But music in general, no. All this moving around in phys ed, I'm not really too keen on. How much time we got?
That was smart.
40 meters per second is our change.
Which one is part
Both of those actually. Now, am I done? Well, no?
No.
Why not? I feel done,
The acceleration.
but it's,
You have the acceleration.
I have the acceleration. It says determine the velocity. Is this really determine the velocity after 4 seconds? Am I not really asking for the final velocity?
Yeah.
And it doesn't come out and say it, but it doesn't say anything about what the initial is. So you kind of got to assume the initial is 0, right? And so, I mean, I'm going to put it in blue because it's kind of optional. But if the change in velocity is 40 and you're solving for VF, but the VI is 0, well, guess what? The final is going to be 40.
So is that necessary?
Well, yeah, you should probably at the very least put that, right? I don't need to see all this. What is the delta V and the VF the same number, AJ? When the VI is 0, correct. Which happens quite a bit.
Triangle B equals VF.
Yeah, you should at least, I want you to at least say that so that I know that you know that delta V and VF aren't always the same. Okay, that seem fair? Okay. How many we got left? Just one more? Or 2? Oh, it's not a tumor. Didn't Arnold Schwarzenegger say that? Do you guys feel like, oh, I was going to ask you if you feel like trying one.
We can try this one.
You want to try this one?
No, I really like that.
Okay. Well, I would be negligent if I let you try this. Because this one's a little different. Yeah.
Try the-
So I want to tell you that there's kind of 2 types of problems, 2 views, let's say. These ones, both, what kind of view is the object? Like, what's the angle that you're looking at? Like this one is you're kind of looking at it sideways, right? Sideways,
Like bird.
sideways, right? These are both sideways. But the third one, Leo's right, this one has south and east. So it's like you're looking
So bird's eye.
bird's eye view, drone view. I wonder when that will be a phrase.
Never.
Never? Bird's eye view, drone view? Okay. Okay. So in other words, it's a top-down view, right? A 100-kilogram crate is being pulled in 2 directions with different forces. 250 newtons south, 150 newtons east. That's your clue that you're looking top-down. It's giving you those kind of directions, like you're looking at a map, right? That's kind of your cue there. So let's draw our crate. And our forces are 250 south, down, and 150 east, like so. Are those both applied forces? Yeah, but there's 2 of them, right? So can I label them both FA?
FA1 and
We could do FA1 or FA2, or even to make it simpler, Leo, could we just go F1 and F2? Is that okay with you? If you want to go FA1 and FA2, that's perfect. Now, there is also
Friction.
Which direction is friction?
But which one is greater? Whichever one is greater, the friction force is applied on.
Okay, so AJ's saying he thinks that I'm going to put it in red. AJ thinks it's like that because this 250 is greater. Is that what you're saying? Okay, Brett's I think is saying it's going to be like that.
Yeah.
Yeah, I got my direction.
Okay, so you want to go to the blue one? Yes, you guys are right. Why is it that way? Because which way are these? What this box is? If it's going to be pulled down this way and that way, which way is it going to go? It's going to go that way, and friction is always opposite the movement. So it's exactly like that. And you'll notice that the F2 is greater than the F1, so it's going to kind of go more down than it is to the right, right?
Yeah.
Okay, so really, we got to add up all these forces. We got 3 of them, and it's in 2 dimensions. Can we add all 3 together at once? Or what's your gut telling you? Okay, Leo thinks we should add F1 and F2 together and then worry about friction after? And Leo would be right. So how do you add 2-dimensional forces? 150, remember you placed them? Remember we're doing the Russian nesting dolls. I'm taking prior knowledge and adding it together. It's kind of like my dad making lunch. He just takes all the leftovers out, just throws them in the pot all together at once.
Oh, heck yeah.
Are you listening, Dad? He doesn't listen to my YouTube videos. Maybe I'll tell him to listen in. Hey, you should listen into this video. You're mentioned. 250 down. Now what? Where is the sum of that? From where you start to where you end, just like we did back in Unit 1.
Tip to tail.
Tip to tail. No. There's the tip to tail. Remember, the final is the final is supposed to be tip to tip, right? So now, what are we going to call that one? It is, right? I mean, if I was doing this, I would call that F1 and F2, and then I would just say this is like the FA. The FA is kind of like the net applied force. You could call it FA net if you want to be complicated. Can we just call it FA? Again, the labels don't matter a whole lot. If I look at it, I'll know what you're talking about. Okay, so don't get hung up on those labels. Don't say, I can't do this because I don't know what to call that. You're quitting when you do that. Don't be a quitter. Okay, so now how do I do this? Is it a right angle?
Yeah.
Sure is. FA squared is equal to 150 squared plus 250 squared. That I'm going to need a calculator to do. I know you think I'm some sort of mathematical wizard, but I can't. Well, I might be able to come close. You're going to help me out? Thanks. 150 squared plus 250 squared. Don't forget to take the square root. It's going to be like about 300 or something rather, isn't it?
350.
How much? No, it won't be 350. I think it's 312.5 if I'm not mistaken. I've done this question many times. You'd think I'd know it off the top of my head. There's a lot of space on the top of my head. I could be. I could just be yakking here while I'm doing the math in my head, but I'm not.
You gotta try that.
291.
290. Oh. Brett tells me it's 291.5. Does that seem reasonable? 150 and 250? Yeah, it should be more than both of those, right? 291.5.
Oh, yeah.
You'd buy that? Only if it was on sale? Okay, now where's the friction? This is the friction right there, right? I listened to Brett, that's what I... Huh?
Way more than that.
No, you gotta take the square root. You gotta take the square root. Right? 155 squared plus 250 squared equals 85,000. And then square root, right? You should be able to do that all in step seconds. You got a square root, right? Yeah, because it's FA squared. Okay. Okay, so now you're going to say F net is equal to the applied force plus the friction force. Now, this FA is at a certain angle. Okay? Can we, for the purposes of this portion, can we just declare that that direction is positive?
Sure.
Yeah.
Yeah, we can. We can do that. We can say that direction is positive, which makes the FA negative, right? We can do that. So all I'm going to do is I'm going to say my net force is 291.5 plus a minus 50. That I can do in my head. Yep, 241.5. You guys are hanging in there pretty good today. I'm pretty proud of you. I'm doing a lot of yakking today. 241.5. And now what? Now we got to find the acceleration. Now we're going to go. F net is equal to F net, not FD, F net is equal to MA, mass times acceleration. And you're going to take that 241.5, and it's going to go in there. And our mass is 100. Oh, that's convenient. And we're going to divide both sides by 100. We'll just say 2.4 meters per second squared. And I just pressed a button I didn't want to. I am not done. And the reason that I'm not done is because acceleration is what kind of quantity? Starts with a V and ends in ector.
A vector.
Vector quantity, which means it has a... So in other words, I got to find that angle there. It's a vector.
You think it's right?
How can you tell?
Well, here's, you know what, Sarah, that's a really good question. She wants to know, oh, it's a good question. She wants to know, when do I find the angle? Here's sort of the rule for that. If the question has north or south or east or west in it,
You got from
you're going to have to use north or south or east or west in your answer. Does that seem okay, Sarah?
Not north, south, east,
Yeah.
west, east,
When they've given you a direction, you got to give me back a direction. Seems fair. I gave you a direction, you should give me one. Because I like direction in my life. Okay. Theta equals, we got opposite, we got adjacent. So it's going to be inverse tan. Yeah, you can do it. Thousands of physics students before you have, and thousands after will as well. You can do it. Opposite over adjacent. Opposite is 250. Adjacent is 150. And that, for sure, I need to calculate for.
Nah.
Yeah, I'm such a...
If you could do that by himself, that'd be a talent.
But we just found it the F net, why would we do it again?
We're finding the angle.
Which way do we go? We can be going 2.4 meters.
Why does your
But we can go in any way we want.
Say again, Leo?
What is your triangle?
Well, it's not to scale, if that's what you mean.
No, like, numbers are.
59 degrees?
Is that what it is?
Yep. So that's going to be 59. Let me just do this, Leo, and then I'll get to you, okay? So that's going to be 59 degrees, but what are the directions that I put in there? And that's easy to do, because what are the directions here? The 150 is east, 59, and then south. I went east, 59 degrees, and then I went south.
Yeah, I'm confused why you get, like, how you
use that?
Because, how do I use tan? Actually, it's pretty much always going to be tan, pretty much. Tangent is opposite over adjacent. I use tan because this is my angle, and I know the opposite, and I know the adjacent. If I knew the hypotenuse, I guess I do, you could use sine and cos, but you'd have to use the 241.5 as your hypotenuse. And that'd be okay. That'd be okay. You could do that. I just tend to use tan because those are the numbers that are given.
Yeah, so you for sure know it's.
Yeah.
How do you know if east first and then?
Usually, when you draw your picture, Junior, like from there, I've gone east first,
First and
right? You go east first, and then you go south. So
What if we draw?
if you drew it the other way, if you went 250 and then 150, right, then you wouldn't get east 59 south. You would, in fact, get south 31 east. These two numbers would add up to 90 degrees. They're both right. They're both right. I'll take both.
The first number is the direction you start with.
Right.
The second number
Yep.
is the end. That's where you go for one.
Okay. I think we're good there. I would like you to try this one. Okay? I would like you to try this one. You need me to go back to that one, Zane? Okay. Let's give it a whirl. The truck has a mass of 1,800. Some of you might find this helps. Writing down M equals 1,800. How much force will the engine need? That I'm solving for FA. FA is the unknown. To accelerate it at 1.75, my A is 1.75. And the friction force, the FF, is 250, but we know it's going to be opposite, so that's going to be minus 250. Okay, so you look at what you got. We got M, we got A. What can I get at M and A? F net. The net force is mass times acceleration. And the mass is 1,800. And the acceleration is 1.75. And I know you did this right, Ty. What's the number? 3150? No.
Yeah.
3150?
Yeah.
3150 newtons. Okay.
So it's 3150, then you have to add the friction because it's got to open up.
Ah. Here's where showing your work and doing the formula will help you, will pay off. Because here's the next step. You write F net is applied force plus friction force. Make sure you plug in the right thing. So the 3150 is my F net, which goes right there. You are solving for FA, and the FF is minus 250. But to solve it, you got to take it back to the left. And so it's going to be 3150 plus 250. Let me write that so you can read it. You don't have to write it down as I do it, Zane. You could just look. I'll wait for you. I promise. You take that 250 on the side becomes positive, and then what is your FA? Sorry, Brett.
Okay.
You'd be surprised if you guys got 3,400. Give yourself a round of applause, because the vast majority of grade 11 students at that point, you know what they do? They instantly go 3150. They subtract the friction, and they get 2,900. Okay? You don't always subtract friction. That is not a rule. What you do is you plug it in this way and you solve it. If you do this, you'll never make that mistake.
Well,
100% guarantee you'll see that question on a test. Guaranteed. Mervin. Good question. Mervin's asking, do we need a direction? Okay, give me 30 more seconds, then I'll be quiet. 30 more seconds. Mervin's asking, do we need a direction? Technically, yes, but because there's no direction given here, we don't really have a reference point. All we know is that there's an applied force that's
say forward.
really forward or positive is good enough, Mervin. Okay, because we're dealing with a positive negative situation, just the positive is good enough, okay? Great question.
We're not backing up.
Right. Beep, beep, beep. Okay.
You'll be a.
Certainly, I have taken a lot of your time. I appreciate your patience.
If the car is moving backwards, left friction is gonna be like,
The friction will be forward.
yeah, but it's gonna be plus or
Yeah.
plus.
Okay. Hold down for a second, you guys. Stay with me here. 10 more seconds. On the back side here, you have a bunch of practice questions. with them is, oh, there is a link in the bottom, excellent.
Yep.
Have to code those, no link, I guess, right? Okay, there are some that say, force at an angle. See like number 7 there, see it says force at an angle?
Yep.
Don't do that yet. Don't do number 7.
Or 8. 2 on the other side.
Right, okay? I'm going to give you the rest of this period. I realize that's not a lot. Depending on where we are tomorrow, I might give you some time, then I might do force at an angle. We'll see how things go tomorrow. I appreciate your patience. We're going to do this for a couple days.
Yeah, that was a
Okay?
good class.
You need to practice.
That was a good class.
40 minutes.